Hello Chem 1A, this is Chapter 8, Lecture Video 8, and we're going to be starting to talk about electron configurations. I showed you the electron configuration of oxygen in the last lecture video, and it's really just a shorthand of orbital energy diagrams. But if we had to draw the orbital energy diagram to write the electron configuration, it really wouldn't be much of a shorthand. So what we typically do is we use the periodic table to write our electron configurations. So if we look at the electron configuration of a couple different elements here, like hydrogen, helium, lithium, and so on, they all kind of revolve around the periodic table. Now we can break the periodic table, and part of the reason why the periodic table is in the weird kind of Tetris-like shape that it is that we've broken it down into the different orbitals that electrons are being put into when we go to a certain element in the periodic table. So these first two columns here are the S block, and technically helium is part of the S block as well. Now, other than the S block, we have the D block here. We have the P block here. And we have the F block right here, right? Now, if we're trying to write the electron configuration of any element on the periodic table, we simply count up to that element by going through the different rows, right? So let's do an example. For instance, let's talk about hydrogen. Well, hydrogen has one electron. So if I were to write the electron configuration of hydrogen, I just stop here at 1s. And specifically, I'd write 1s1 for the electron configuration of hydrogen. Now, helium, we do, okay, this is 1s1 here for hydrogen, but helium, we continue on to this element here. Well, this is the second 1s electron that we'd put in here. So helium's electron configuration would be 1s2. Now, lithium is the next element in the periodic table. It's element 3, right? So when we talk about lithium, we're talking about this elemental square right here. Now, we still start at 1s1. Now, here's the thing, though, right? If I'm trying to get to lithium, I know this is 1s1, this is 1s2, and this is 2s1. Now I have to combine all of this, so every time we finish a row, we just use that value and record it. So now lithium would be 1s2, 2s1. Now if we look at beryllium, beryllium is the second element in the 2s block, right? The 2s row. So we're talking about this element here when we're talking about beryllium. So Be is going to have all the electrons of lithium, helium, and hydrogen, but now this is 2s2, right? So beryllium's electron configuration would be 1s2. Again, we fill the whole row from the previous row, which would be 1s2, and then it'd be 2s2. Now, if we go to boron, boron is this elemental square, B. And it's going to be all of beryllium plus one more electron. But this electron is in the 2p block. So when we write this guy's electron configuration, it'd be 1s2, 2s2, 2p1. Right next to boron, let's do a different color here. Right next to boron is carbon. And so carbon would be the same as boron's electron configuration, except an additional 2p, right? So this is 2p2, right? So it'd be 1s2, 2s2, 2p2. Now this would continue until we got all the way over here to neon. Neon is the last element in this row, right here. And so if we count, right, all of our electrons, we're going to do all the ones from the before. So we have 1s2, 2s2. Again, we're doing that by going, okay, well, I have 1s1, 1s2, and this is 2s1, 2s2, and then this would be 2p1, 2p2, 2p3, 2p4, 2p5, and this is 2p6. And so I'll finish off neon's electron configuration by putting 2p6. And so we can kind of just keep doing this in a way and counting up to the correct electron configuration by using the periodic table. So let's do the last one on this list, iron. Iron is the sixth element in the 3D row. So 1, 2, 3, 4, 5, 6. This is Fe here on our periodic table. Now, if we're doing this electron configuration, again, we're going to start from the very beginning. So anytime we complete a row, we fill that orbital all the way, right? So for instance, because iron is not in the period 1, then we're just going to fill that entire orbital sequence, which would be 1s2, right? Iron is also not in the 2s block, so this one's 1s2, and then this one would be 2s2, so I'm going to write 2s2. It's also not in the entire 2p block, so I'm going to fill that. That would be 2p6. It's not in the 3s block, so this is 3s2. And it's also not in the 3p block, so this would be 3p6, right? So if we continue writing this out, right, it's 3s2, 2p6, and now it's also finally not in the 4s block, so this would be 4s2. It, however, is in the 3D block, so now we just got to kind of count. So it's going to be 3D1, 3D2, 3D3, 3D4, 3D5, and iron is 3D6. And so I'm just going to add that to my final little bit here, 3D6. And so this is my electron configuration of Fe. And so that's kind of how we can write our electron configurations. Okay, so let's do a couple more practice problems. Now it helps if we have a periodic table, so I'm just going to kind of fake one. Like that. All right, so if we're talking about F is in the second row of the periodic table, and it's right there. It's in row 2, and it's right next to the noble gases. All right, so if we think about that, and if we're following along on the periodic table, it's not in row 1 of the periodic table. So we know 1s is just going to be part of its electron configuration. It's not in the s block at all. So 2s, it is in the second row of the periodic table, but it's not in the s block of the second row. So we're just going to fill the s's. So that's 2s2. It's going to be in the 2p block. And in fact, it's the second to last element in the 2p block. So if we count across the periodic table, right, it'd be 1, 2, 3, 4, and this one would be the fifth block, or the fifth square in that p block in energy level 2. So that's why we have 1s2, 2s2, 2p5. Selenium is a bit lower down in the periodic table. It is in the 4th row of the periodic table. So we have a bit of a ways to go. So, right, if this is row 1, this is row 2, this is row 3, I have to kind of, again, I'm using a bad periodic table. This is row 4, right? And so these are our noble gases. Here is fluorine. Here is oxygen. This row. This is O. This is F. This will be N. And then we have like B and C, C and B. So if we're looking at this, this is selenium right here, Se in the fourth row in the column that oxygen is in, right? And so we know that all these early rows are going to be just fully filled. So we have 1s1, 2s2 because it's not in the 2s block, 2p6 because it's not in the second row at all. It's also not in the third row, so it's 3s2, 3p6. It's in the fourth row, so this is 4s2 because it's not an s block element. It's a p block element. So we're also going to fully fill the d block, which means 10. If we count across the d block in the fourth row, you count 10 elements. So 3d10 is the max we could put in our d block, which is also how many we can put in based on quantum numbers. It is in the 4p block, and if we count across, it's going to be 1, 2, 3, 4, right? It's the fourth element in the p block in that row, so it's 4p4. Astatine gets even harder, and if you follow, I'm not going to draw it on the periodic table, but if you follow along, it's in the 6p row. So it's a p block element in the sixth row of the periodic table. What this means is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2. I'm going to erase my periodic table at this point. 5s2, and then 4d10, 5p6, because again, it's not in the fifth row, it's in the sixth row. So now we go, okay, great. Now it's 6s2, and here's where things get tricky when we're in the sixth or seventh row of the periodic table. After 6s comes 4f14, because we got to account for those f block elements. Even though they're not part of the main periodic table, they are a significant part of our electron configurations. And so 4f14 follows 5d10 and then 6p, and we count over, it's going to be 6p5. And so this is a bit more tedious, but if you're just counting along with me on the periodic table, it should be relatively easy to follow. Iron we did at the end of the last one. I don't know why I include this as an example, but it would be 1s2, 2s2, because again, iron is in the fourth row of the periodic table in the D block, so we know we're going to end on 3D something. And so then we have 2p6, 3s2, 3p6, and then now we have 4s2, and then 3d, and now if we just count over to Fe from scandium, which is the first element in the D block in row 3, you get 6 elements over, which is the electron configuration. Now, that second to last one there, astatine, AT, as you might have noticed, that was a heck of a lot of writing, and it was a little bit repetitious. So there is a shortcut to elements that have really, really long electron configurations that we really don't want to show every single little electron in, and it's called the noble gas notation. So let's look at the electron configuration of nickel. Now, if we write out electron configuration of nickel, it's 1s2, 2s2, 2p, 6, 3s2, 3p6, 4s2, 3d8 is the electron configuration of nickel. Now that's great, but now let's write out the electron configuration of the noble gas previous to nickel. So the noble gas that's in the row before nickel is argon. So if we write out argon's electron configuration, it's 1s2, 2s2, 2p6, 3s2, 3p6, and that's argon's electron configuration. Now, I don't know if you guys notice, but that part of nickel's electron configuration and argon's electron configuration are identical. And so this is a way we can shortcut the process. Now, how can we do that? Well, we can write in brackets argon. So if we want to write the electron configuration of nickel using noble gas notation, we'd write brackets AR. Now what this brackets AR is supposed to reference is this whole part of the nickel electron configuration. So we'd write brackets AR, and then we're just going to write what's left, which is the 4s 3d8. It gives us a way to shortcut to the end. All right, so let's practice using the noble gas notation for electron configurations. So we did astatine's regular electron configuration in the previous couple slides back. So let's look at that, and then we can kind of tell why noble gas is so valuable if we just look at astatine, how much you have to write when you're doing the normal notation versus the noble gas notation. Okay, so here is the electron configuration we wrote earlier. A lot of writing to do. But if we use the noble gas notation, this is a heck of a lot simpler because we're going to use the element, the noble gas, that's in one row up from astatine. Always the row before the element we're writing the electron configuration for. So the noble gas above astatine, one row, is xenon. So we're just going to write Xe. Here, I'll do it in a different color. Brackets Xe, because that's the noble gas one row up from astatine on the periodic table. And then we're going to just kind of count from there. So that we finished up to basically here is where we finished up to. So we really need to only write what's left. Now, if we're following along on the periodic table, right, that means the 6s is next after xenon's done. And astatine isn't in the 6s kind of two elements there. It's cesium and barium, and neither of those is astatine, so we're just going to fully fill that. We're going to write 2. After 6s, it's always the tricky one. You got to make sure to write 4f14 because 4f, we do the 4f orbital after 6s according to our filling rules that we learned in the previous lecture videos. Astatine, again, not an 4f element, so it's not in that row, that first row of the F block. And so we're just going to fully fill that F block. And so that's just 4f14. After that, it's the 5D according to our filling order. And astatine is not a D block element, so we're just going to fully fill this D block, the 5D10. But it is a P block element in the 6th row. So now we just need to count over from thallium to astatine. So thallium's 1, lead's 2, bismuth is 3, polonium's 4, and then 5 is astatine, so it's 6p5. This is a heck of a lot less to write than the top one. This is why we use noble gas notation, especially most often we use it for elements that are a bit further down on the periodic table, like astatine. And so this is the more common use. So let's do another one. Let's talk about strontium. Strontium is in the 5th row of the periodic table, which means if we want to use the noble gas notation here, we need to do brackets, the noble gas in the row above strontium. So that would be krypton. Krypton is the row for noble gas. And we're just going to start counting in row 5 then. So the first ones are the 5s, that's rubidium, and strontium. And so strontium's the second element, so this is just krypton 5s2. That's all we got to write for strontium's noble gas electron configuration. Now, if we wrote the full electron configuration of strontium, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and then 5s2. This is the full electron configuration of strontium. I don't know about you guys, I'd much prefer to write the noble gas notation in this case. Now, you will need to be able to do both of these. In fact, on our next test, I will be saying things like, in the problem, write the following electron configurations using the noble gas notation or without using the noble gas notation. So you'll be kind of told what to use and when. All right, so our last element here is zinc, and it's in the 4th row, which means we need to use the noble gas from the 3rd row, which is argon. So I'd write brackets argon, and then we got to ask ourselves, okay, is zinc Potassium or calcium? No, so it's not a 4s element, so we just write 4s2. It is, however, in the D block. Zinc is the last element in the D block, so this would be 3d10, and that is our electron configuration. Okay, so I know this has been a long video with a lot of practice, and electron configurations are all about practice. So the more you practice them, the better you'll get at them, and they're really not too bad if you just know the rules and know how to apply them. So if you have any questions, of course, you can always ask in the problem-solving sessions or my office hours or email me. I'm always happy to answer anybody's questions.